We have the differential pair driving a common source amplifier M11. Okay. The output is connected to a load, parallel combination of R and C, and it's connected to some bias voltage. Okay. We looked at the frequency response of this stage yesterday. Yeah, this is the schematic, and the DC gain is given by this expression. And the poles and zeros are given here. Okay. The unity gain frequency is approximately the GM of the first stage divided by the compensation capacitor CC. Good. Yeah, and the expression is here. Okay, and there is also a right half plane 0, which comes because of this capacitance, which is connected across M11. Okay. So the right half plane 0 also tends to worsen stability. So what do we do about it? We can connect a zero cancelling resistor in series with the capacitor. And what's the value of RC that's required? 1 by GM11. So at this value, the 0 disappears completely. Of course, if you now look at it, the order of the transfer function would have increased by 1. But for a small value of RC, the extra pole that is created is at a high frequency. So it doesn't matter too much. Okay. So this is the standard topology for two-stage op-amps that's used. We have a differential amplifier driving a common source amplifier, and you use capacitance across the second stage for compensation. And we have a resistance in series with the compensation capacitor so that the right half plane 0 is cancelled. Okay. Now, if you use a physical resistor, let's say made of polysilicon, the process and temperature variation of this will be very different from that of this. So you have to simulate it over the process corners and make sure that it does work. Now there is a certain type of biasing where you can make the GM of M11 constant with process and temperature. If you use that, then if you make it inversely proportional to R, then this condition is satisfied. Okay. An alternative is to use a MOS resistor here. Okay. You can use a MOS resistor, so any variations in the MOSFET will be tracked by the variations in the resistances also. Okay. So that is also a bit of a problem. We can so would I use a PMOS or NMOS here? For good tracking, I should use PMOS. Okay. Now I can tie this to ground. That is one possibility. But then the voltage at this point is what? Yeah, it will be VDD minus VGS11. Okay. So what is the gate source voltage of this MOSFET? MC? VDD minus VGS11, and it's sensitive to the supply voltage variations. That is not a very good thing. So you can of course try to generate this bias voltage so that it's a fixed value. I mean, it is equal to, let's say, this bias or something like that. Okay. But without doing anything more complicated, I would just tie it to ground. Alternatively, you can use an NMOS. And tie this to VDD. Then the gate source voltage of this always tracks the gate source voltage of M11. But of course, it's the opposite type of transistor. So both ways there are some problems. But we can use it with some care. Okay. No, you want the resistance of this device to track the reciprocal of GM of this. So if you have NMOS and PMOS, they won't track as well as if both were PMOS. I forget. I have to work it out and I'll let you know. Okay. I'll in the summary of the characteristics, I'll act as though that was not there. Okay. What are the poles that I'm going to list are the values without this RC. Okay. The unity gain frequency is mostly this. There is this modifying factor. Okay. Where, what is CP? CP is the parasitic capacitance at the output of the first stage. Okay, from the output of the first stage to ground, which consists of CGS11, CDB3 and CDB1. Okay. So if CC is rather large compared to CP, then the unity gain frequency is approximately GM1 by CC. Okay. The second pole is at I'll ignore GDS in this expression. Okay. It also contributes to the output conductance, or maybe I'll put it, but you can expect it to be smaller than GM11. Okay. And there is a mirror pole and the 0. Maybe I should put the other one first. This is the right half plane 0. But this gets cancelled when you use RC. Okay. Yeah. That's true. With the 0, you will have to make GM11 higher, but you can't make GM11 very low. We'll see that. Okay. So even with RC, you can't make GM11 much smaller than GM1. Okay. Yeah. Yeah, that's correct, but the CGD can be expected to be smaller than the CC that you put there. Okay. Yeah, there will be something else, but that will be small, right? The other 0 will be at a high frequency also, because the CGD is small to begin with. Okay. What he was pointing out was that there is some intrinsic CGD of M11. It does modify the frequency response, but it just gets analytically too complicated to see it with expressions. But one thing is, if the CC is much more than this intrinsic CGD, you can expect the effect of this to appear only at much higher frequencies. Okay. So in reality, this means that when you simulate it, your results will be slightly off, but you have to figure out exactly why that is. Okay. Like when you have a significantly large CC, then the effect of CGD is not there so much. Of course, it will cause a 0 still, because there is still a feed-forward path between the input and output of M11, but it will be at a higher frequency. Okay. So what do I do? So one thing is, the one possible design path is, I already have, let's say in your case, you have a differential amplifier of a certain gain of 50, okay, and you are asked to make a two-stage amplifier of gain 500, I think, 500, and the load resistance is given to be 5 kilo ohms, okay. If I choose to use exactly the same first stage, so this is exactly what you have designed, perhaps a scaled version of it, meaning you scale all the widths and also the bias currents. If you do that, the DC gain doesn't change, right? Then I connect it to a second stage. Now this provides a gain of 50, this provides a gain of 10. Now a gain of 10 is probably still too much for a second stage, but let's assume that we have done it. Okay. If you do that, you know the load resistance. Okay. So what should be the GM of this? What should be the GM here? Yeah. 200 micro Siemens. Okay. So essentially you know this MOSFET. You know M11. Because you know what quiescent VGS there is, and you know the GM you want, so you know the size of the MOSFET. So you make the MOSFET. And of course, you also make a suitable current source on the other side. Okay. How much current would be required here? An estimate of the current. That actually swing will, in fact, make the current more. But just looking at this, right? You have GM of 200 microsiemens. And let's say you have VD-SAT of 200 millivolts. I don't know. I'm just guessing. So 2 times ID by 200 millivolts is 0.2 millisiemens. Okay. What's ID? $20 microamps. Yeah. So this is a small current, but like I said, if you to get a signal swing, because right now this is just a quiescent GM11. Okay, you need at least this much, but to drive a signal into this, you need a large quiescent current. Okay. So let's say you have some load impedance. Okay, this is connected to some quiescent bias. Okay, now this is the same as the output bias when it's put in feedback loop, so that no current flows in the quiescent condition. That's the idea. What is the maximum current that can flow out of ZL? Flow into ZL rather. Huh? Why? No, what is the maximum current that can be supplied by this circuit? Huh? No, I didn't say that the quiescent is 20 microamp. Let's talk in general terms. Is there some limitation? I naught. Why? Okay, what's the current that can be drawn back this way? It's a bias current. Okay, because this current is the difference between the current in M11 and M12. Okay. So to get the maximum negative current or maximum current drawn out of the load, you need to have minimum value for this. So essentially, if this voltage goes very high, this almost cuts off. Okay, so the maximum current is the bias current of M12, that is I1. That is equal to I1. What is the maximum current that can be pushed in this direction? No, that is the current that flows because of the load. But what's the capability? I0 minus? Actually, it is not limited like that, right? So this voltage can go down, right? So it can go down all the way to, depends on the swing limit of the first stage. So it depends on that, isn't it? It's not limited to I0 or anything like that, because this voltage can go down. So as this voltage goes down, depending on the characteristic of this transistor, the current here will go on increasing. Okay, this current is fixed because it's a current source. So at some point, of course, this voltage will not be able to go down any further and you hit a limit. But the limit on the positive current is more benign, meaning you can increase that current by lowering this voltage. Okay, whereas the current that can be drawn out is limited by the current source value M12. This is okay? This is a characteristic of a common, class A amplifier, right? Let's say I have something like this. The output is the difference between the current in M1 and the bias current I0. And what is I1? I1 is nothing but mu Cox W by 2L, this VGS minus VT square. So I can draw any current I want from the load. Subject to the limitation on VGS. Okay, at some point VGS itself will get limited, or also this may go on increasing, but this goes into triode region. Okay, then the current won't increase anymore, at least not as a square law. Okay, so there is some limitation based on the limit on VGS and the output swing, but the other side is limited to I0. Okay, so this is the characteristic of a class A amplifier. On one side it's not limited, the other side it is limited. Now you are most of the time interested in driving symmetrical signals like a sine wave. So bottom line is, overall the current here is limited by I0. Okay. So this is always true of class A amplifiers. Class A amplifier is driven on one side and there is a bias current on the other side. The bias current is a hard limit. The other side you could have possibly pushed more current. Okay, you still have to make sure that you can do that, but it looks like by raising VGS I can increase the current, whereas the other side I can't do anything like that. So because it is limited on one side, for symmetrical signals, that means the peak value is limited. Okay. So to get a desired peak value, you need to have a sufficient bias current in the output stage. Okay. Now that is what the stage can provide. Now you need to see what the load needs. Okay, that depends on the swing here. you have a certain swing at the output. The peak to peak swing divided by the load impedance at the frequency of interest will give you the peak to peak current. So half of that peak to peak current must be the bias source, at least half of that. It needs to be a little more than that. Okay, things cannot completely cut off. Is this okay? So in our particular case, let's take only the resistive load. What is the swing that is possible here? What are the swing limits of a two-stage amplifier? So it's approximately VDD minus VD sat on the upper side, and on the lower side it's VD sat 12 and this is VD sat 11. I say approximately because as this voltage is rising up, this voltage is falling, right? So you may have to take that into account, especially when you have a second stage with a very low gain. Okay. When you can make second stage with gain of let's say 3. Then for an increment here, there will be a significant increment here in the opposite direction. So you have to take that also into account. But let's say for a gain of 10, we ignore that. We assume that it's VDD minus VD sat 11 and VD sat 12 here. Okay. And let's assume our usual 200 millivolts for VD sat. So this can go up to 1.6 volts and go down to 0.2 volts. So because you have only one transistor on each side, a two-stage amplifier is capable of a very large swing. Okay. This you could not do even with the folded cascode. So far the best swing we have seen is from the folded cascode. What is the swing available in the folded cascode? Let's assume all VD sats to be the same and let's say 200 millivolts. So you lose 2 times the overdrive voltage on each side. Okay. Because you have 2 transistors on top of each other. Whereas here you lose only 1 overdrive voltage. Okay. Okay. So let's say we have 1.6 volts and 0.2 volts. So this corresponds to a 1.4 volt peak to peak sine wave, right? This is the largest sinusoid that can be accommodated. Now if you pass this through a 5 kilo ohm resistor, what is the maximum current that needs to be pushed or pulled? What is it? So it's 700 millivolts peak divided by 5 kilo ohms. Okay. That is 140 microamps. So you need at least 140 microamps. You can expect currents of the order of 150 to 200 microamps in the output stage to be able to accommodate this. Okay. So clearly you can say if the load resistance decreases and you have to support the same swing, you have to use more bias current, obviously, right? Similarly, if the load capacitance increases. So if the load capacitance increases, also the current will increase. Or if you have everything the same, but you need to scale it up to a higher frequency, then for the given load capacitance, you have to push more current. Then also the current in the output stage increases. So, but this is how you go about designing the output stage. I think you already have most of the parameters that you need. You bias it around 150 microamp, make sure that it has a GM of 200 microsiemens. Okay. And you connect up everything, it should work. Is this okay? Any questions on the swing limit or the drive capability? Now, this is relevant even for the other op-amps, the differential pair and so on, but usually they are not very useful for driving resistive loads or heavy loads. That's why I didn't take that into consideration. But there also you will have capacitive loads, and whatever current you have in the capacitive load must come from the stage. Okay. So you have to have a certain bias current even in the telescopic and the folded cascodes. That depends on the load capacitance. This is okay? Yeah, so let's see how to do that. So let's say you chose the output stage. Okay, you can design backwards, starting from the output stage. I mean, this of course assumes that the gain of the second stage is fixed, which also is subject to change, right? You can design anything you want. But let's go with the assumption that I want the second stage of gain 10. Okay, after that you can change it if you want. you source the desired bias current from M12 and you choose M11 for the desired GM. Okay. Now this is of course given the load. Then what do you do? What is the total current consumption of the two-stage amplifier? I0 plus I1. It's I0, the bias current in the differential pair, plus I1, the bias current in the second stage. Okay. Now, I want to obviously minimize the power consumption. So, what do? I scale down I have the output stage, but I scale down the input stage. By scale down, I mean scale down all the widths and all the currents. Okay. So, what I can now do is, I take a scaled down version of my differential pair. Scaled down or scaled up? I will just say alpha times GM1. Okay. What is the capacitance I put? I want a certain unity gain frequency, right? So, I have to have a certain capacitance corresponding to that. Okay. So, what is that? Omega u is alpha GM1 by Cc. Okay. So, this is alpha times GM1 by omega u. So, what do if I want to reduce the current consumption? I use a small GM and a small Cc here. Okay. So, I have my stage, I can connect it up. Now, I can use a scaled version of that also. So, I scale it down as much as I want. Can I scale down indefinitely? Is the process clear or not? I want to add a first stage to this. That's how I am approaching it. That's not necessarily, you can also start from the first stage perhaps. But I have designed the second stage for a certain gain. Okay. Then I have some sizes. Okay. Then I add a first stage to it. Now the first stage, I want to minimize the bias current clearly. But I want to of course maintain the given unity gain frequency. So, I connect this GM and this capacitor here. Okay. And also, okay, a zero compensation resistor. What is the value of alpha I will choose? Like where will I stop? Can I make alpha indefinitely lower? So, what happens is that if you look at the expressions for, see, what is the condition? This is my omega u and this is my P2. Okay. First of all, I have a certain specification on omega u. I have to maintain that. Right? To get a certain speed of the negative feedback system, I have to maintain a certain unity gain frequency of the op-amp. And of course, the P2 must be beyond the unity gain frequency. So, what happens if you keep on reducing Cc? First of all, omega u itself tends to reduce a little bit. Okay? And also, what happens to this? P2 keeps on moving in, right? Because Cc is the pole splitting capacitor. Now, this parasitic capacitance Cp at the output of the first stage depends on the first stage itself. So, that is proportional to the first stage width or the first stage scaling factor alpha. But it also has CGS12, which is fixed. Okay. I can scale this part, but I can't do anything about the CGS of this. Once I have chosen M11. Okay. So, if I go on reducing Cc, Cp will reduce but not in the same proportion. Okay. So, the conductance in the numerator will go on changing. So, but the denominator changes a little bit. Okay. So, in fact, this will go on decreasing and the load will dominate. So, P2 also will keep on moving to lower frequencies. So, this means that at some point you will not be able to compensate the op-amp. Okay. So, that's when you stop. Obviously, your goal is to minimize the current consumption. Okay. Now, the total current consumption is I0 plus I1. You can ask, why don't I minimize I1? Why don't I make the second stage very small? But we have already said that we need a certain current in the second stage. Okay, it could come from the swing constraint if you have a resistive or a capacitive load. Okay, so to drive that you need a certain swing. Also, if you make I1 very small, okay, then if GM11 is very small, again the second pole will be at a low frequency. Okay, so you can't use that condition. So typically the second stage current is more than the first stage current, and the compensation capacitor is smaller than the load capacitor. Okay. If I take an extreme case where Cc is much more than Cp, what is this value? What is the value of omega u? Gm1 by Cc. Okay. What's the value of P2? When Cp is much more, Cc is much more than Cp. So I'll ignore everything else, okay. So this is approximately 1, right? And this I neglect completely in favor of Cl. So this is, Gm11 by Cl. Okay. So Gm11 by Cl has to be more than Gm1 by Cc. And the total current is I0 plus I1. Okay. Now the Gm depends on I0, depends also on how you scale the width. Okay. Let's assume that when I change the bias current, I also change the width in the same proportion. That is, I keep the current density the same. So in that case, what happens is the Gm is directly proportional to the bias current, right? So Gm1 by, this is proportional to Gm1 and this is proportional to Gm11. Okay. Let me rewrite that. And the current is I0 plus I1, which is basically some K1, which depends on the current density times Gm1 plus K2 potentially, or maybe K1 and K2 times Gm11. K2, maybe the current density is different, so I have put a different constant there. So I have to reduce either of these. Which one will I reduce? Okay. We discussed it just now, we will look at it in a different way. Can we discuss, can we reduce I1 indefinitely? Why not? See, the point is CL is fixed. CC is something you choose. So if you reduce Gm1, you can reduce CC and still maintain the same unity gain frequency. Approximately. We know that it's not completely possible because the higher order terms will come into picture. But at least to a first order or a zeroth order, we can simply reduce Gm1 and CC and everything stays the same. Whereas here you can't do that. The moment you reduce Gm11, your second pole will move in. Okay. So you can't reduce the second stage current beyond a certain stage. So a typical design will have Gm1 smaller than Gm11 and CC smaller than CL. Okay. That's an efficient design. What's that? We need VD sat of 11. Yeah, that's correct. We can change K2. But how much will you change it? Yeah, that's right. So there is a certain limit. Okay, then now the next, what the argument that he is giving is that I can operate at a lower current density, right? Meaning I'll move closer and closer into sub-threshold so that for a same current I get a larger GM, or to realize the same GM I get a smaller current. Okay. So this now goes into a lot of design detail. First of all, is your current limited by signal swing? If that's the case, you can't do anything, right? It's not related to GM. There are several constraints on current. You have to be able to realize a certain GM so that your parasitic pole is at a high frequency. Second thing is you have to be able to support a certain signal swing. If it's limited by swing, you can't do anything. If it is limited by GM, you can do it. But what happens here? So let's say I have a particular design already, okay, which is working. And let's say all MOSFETs are in strong inversion. Then what I can do is, this is I1. So I keep on reducing I1. So let's say I1 goes to some alpha times I1 where alpha is less than 1. And the width and widths of M11 and M12, I make it. If it's in strong inversion, the GM will be maintained. So what happens because of this? Yeah, it will go down, but is there some disadvantage that you see? See, finally I want to make an op-amp which is stable and which satisfies, basically which is stable, okay, and which satisfies my speed constraint on omega u. So what will change because of this? So this Cp here will go on increasing if I go on increasing the size of M11. So even if I am not constrained by swing, I can't do this too much. Beyond some point, what will happen is the parasitic pole here will parasitic capacitance here will become significant. Then the pole will move to lower frequencies. But that's how it is. This is how you optimize it. But beyond some value of alpha, you can't optimize. That's what it means. Okay. So this is true of every circuit. You take every circuit, maybe the first thing you should think about is this the optimum as far as current consumption is concerned? Of course, there are many other specs, but current consumption is almost always a fundamental spec. So you can try to reduce it. So one way of reducing it is, of course, if everything is operating in strong inversion, then I increase all the widths and reduce all the currents in the same proportion. Then I maintain all GMs. So small signal wise, the circuit will remain the same. Okay. So there are two things. First of all, the parasitic capacitances will increase. So the small signal high frequency characteristic will not remain the same. So that may stop you from doing this. And finally, maybe it's a very low speed circuit, you don't care about bandwidth at all. Then what's the limit? You will hit the sub-threshold region where this won't work anymore. Meaning, you reduce the current and increase the width, the GM reduces. Okay, GM is not dependent on the aspect ratio in sub-threshold region. Only in strong inversion is it related to the product of current and width. Okay, so once it reaches weak inversion, you can't do anything. That's the lowest current that you can design it for. Is this okay? Any questions on the two-stage op-amp? Now I will not discuss some of the other things too much, but one thing I will mention is that the noise and offset of this, what do you expect it to be? Which components will contribute to the noise and offset? What about the contribution of M11 and M12? Okay, I am talking about the input referred noise and input referred offset. Which one will be more significant? Will M1 contribute more noise or M11? Whether you take the input referred noise or the output noise, it doesn't matter. Which one will contribute more? First of all, generally it's always the input stage that contributes. If you look at the input referred noise, then the noise current here will get divided by the GM of M11 and the voltage gain of the first stage. Okay. Whereas the noise of M1 is divided only by the GM of M1. So the contribution of M1 is much more significant. Basically, you have an amplifier. you have an amplifier between these points and here. So anything that is added after this will get divided by the gain of the first stage. Okay, so its contribution will be insignificant. The contribution of M1 and M12 to noise, it will contribute noise directly to the output. That's correct. But if you look at M1, it will contribute noise here, and that gets amplified by M11 and it goes to the output. So the contribution of the first stage is much more significant. That is exactly the same is true for the offset. So the expressions for noise and offset will be the same as that of the simple differential pair. Okay. Plus you will have an extra term because of M11's noise getting divided by the entire gain of the amplifier. Okay. So do we need to discuss this further, or is it clear? This noise stuff. Okay. So first of all, to analyze the noise, I will remove the input signal. Okay. And also, just for simplicity, I will analyze it at DC. Okay. I will not do it at very high frequencies. I will not evaluate the frequency dependent spectral density. So I may as well ignore the capacitor. Okay. So there are a couple of ways of doing this. Okay. First of all, let's take the noise of M1. Okay. This is IN1. Now, I need to calculate the noise voltage at the gate of M11 because of this one. Okay. So what will be the noise voltage? How will I find out the noise voltage here because of this current? Previously we analyzed the noise current. We terminated the output of the differential pair in an incremental short circuit and analyzed it. Okay. How will I find the noise voltage here? How will I do this? Into gain of which one? So there are a couple of ways of doing it. First of all, I can reduce this to an input referred quantity and multiply it by the voltage gain of the first stage. Okay, that's one thing. The other thing is we still use the same analysis. What we analyzed previously was, I terminate this in an incremental short circuit and find the current. What is that current? IN1. This is familiar, right? I get the short circuit current. And I also know the output resistance of the first stage. Okay. So I can multiply the short circuit current with the output resistance and get the voltage. So what will be the voltage here? Will it be plus or minus? Minus. Why? This plus, right? Current tends to flow outside, which means that it will flow into the output resistance. So this voltage will be, is it clear? This voltage will be IN1 by GDS1 plus GDS3. Okay. Now I can again take either the output voltage or the current. So let me ignore the capacitor. What will be the output voltage here? This into the voltage, the output voltage. It will be the voltage gain of the second stage. It is GM11 divided by the total conductance that's connected. Okay. That is the output voltage because of ion 1. Okay. Now, let me take ion 11. So, if I take ion 11, what's the output voltage because of ion 11? I mean, I'll take ion 11 alone. That is the noise of M11. It's minus one, ion 1 divided by the entire conductance, okay, minus ion 11, sorry, divided by so which of this has a larger contribution? So if you compare it to this particular value, there is an extra factor, okay. First of all, ion 1 itself is different from ion 11. Ion 1 is related to the GM of M1, ion 11 is related to the GM of M11. Even then, there is this large factor GM by GDS1 plus, I mean, something of the order of GM by GDS. So ion 1 will certainly contribute more. Now I want to refer it to the input. What do I do? Divided by the gain of the whole thing, which is this. Okay. So this is the voltage gain of the entire stage. What I have taken is the output noise voltage. So to refer it to the input, I divide the sum of these two, okay, divided by the voltage gain. So what do I get? I'll get ion 1 by GM1 minus ion 11 by what? Okay. So now I have taken only one of M1, M2, M3, M4. What do you expect the contribution of M2 to be? Similar to that of M1, and M3 and M4 also, all the noise currents will add up. Okay. And what is the contribution of M0? Nothing. It will contribute in common mode. What's the contribution of M12? Same as M11. Okay. So I think now without more analysis I can write this down. It will be ion 1 minus ion 2 plus ion 3 minus ion 4 by GM1 minus okay. So in terms of spectral densities, what do I get? Here, this part will give me the expression I had before, 16 by 3 kT by GM1, 1 plus GM3 by GM1. I mean, this is exactly what I had for the differential pair. And what am I going to get here? What is the spectral density because of this term? So it's 8/3 kT by GM11, 1 plus GM12 by GM11. Okay. This is of the same form as this. and that's because you have M1 and M2 forming the amplifier and M3 and M4 forming the load. Here you have M11 as the amplifier and M12 as the load. Okay? So you get this GM12 by GM11 ratio. But this is further multiplied by this. Okay? So first of all, you expect GM11 to be larger than GM1. Okay? And let's say for simplicity, GM3 and GM1 are the same, and GM11 and GM12 are the same. So this part of it and this part of it will be the same. Now it's multiplied by a very small number. Okay? So we can very safely neglect the output of the noise of the second stage. You can do this in simulation also. You know how to plot the noise summary from different components, and M11 and M12 should be at the bottom of the list if you have designed the op-amp correctly. Okay? So the similar thing holds for mismatch. Now the only other thing that's left to do, and which involves some reasoning, is the slew rate. So we'll discuss that on Friday. Think about what the slew rate of this op-amp is going to be. Okay? I mean, what limits the slew rate? Why would it be limited? Any questions?